Hello, everyone. Welcome back. Today, we're going to be discussing probability in more depth by talking about the probability of what are called compound events. I'll explain what those mean. So first, our goals are, as it says, to be able to find the probability of one event or another, and then be able to find the probability of one event and another. We'll see these are both types of what are called compound events, and we'll understand the differences in both these and then how to find them. So first, let's explain what a compound event is. As a compound event is any event combining two or more simple events. So with your knowledge of probability so far, the idea of a simple event would be like flipping one coin, drawing one card from a deck, something like that. And then these examples would be, for example, flipping two coins, that's combining, or flipping the same coin twice, combining two events, rolling two dice. Okay, so drawing just one die, or drawing multiple cards from a deck. And this can be, has to be more than one, but it could be many. It could be flipping many coins, for example. The idea is we're combining or doing more than one simple event. And because of that, then the way you think about the probability changes somewhat. It's still the same concept as the number of events we were looking for out of the total number of events. We have to kind of understand better how to calculate the number of events we're looking for. So the first one is dealing with or, and this is what's called the addition rule. So if we want to find the probability of event A or event B, then here's our general rule. We add the probability of A happening by itself, plus the probability of B happening by itself, then minus the probability of A and B happening at the same time. And this is, we explain, this is kind of an idea of overlap. So let's kind of explain this intuitively. It says to find, I'll just read this, P of A or B, find the sum of the number of ways event A can occur and the number of ways event B can occur, adding in such a way that every outcome is counted only once, then divide by the total number of outcomes in the sample space. So be careful of double counting. Now, events that are disjoint or mutually exclusive, they cannot occur at the same time. So if events are disjoint, it means that there's no overlap. There's no way A and B can happen at the same time. So let's come over here to the right and kind of draw an idea of what we're talking about and use a Venn diagram to help us out. First, let me put a little space here. Now, let's draw a box. And this is kind of our set of everything. So here, let's say this is the number of, for set A, the number of ways A can occur. Okay, whatever A is. This is the number of ways event B can occur. And here, then the overlap then, the spot right in the middle, is basically A and B, the ways that A and B can happen at the same time, if it's possible. Now, if they can't happen, if it's impossible, then this is actually empty. There's nothing there. Okay. Then on the outside, then, we can think of this in the box, but not on the outside of both circles. This would be not A or B. Okay. Neither A or B occurring. Okay. And 1 minute. Just a second, let me move that up some. Okay. Then I'll just say if A and B are what's called disjoint, there's no overlap. So here we draw, the picture makes it look like it could be an overlap. This could be what's called empty. So if A and B are disjoint, then the probability of A and B is 0. Okay. If there's nothing there, if there are no events where A and B happen at the same time, and of course, the probability of A and B happening at the same time then have to be 0. Now, let's look at an example to help us with this. And we'll do an example that's very similar to the picture we just drew here, but actually put some numbers to it. Let's look at this below. In fact, I might move this down a bit further. So here's our example. Here's our situation. There's a recent survey of 50 people found that 23 people only like dogs, 15 only like cats, and 7 like both dogs and cats. Let's draw a Venn diagram to summarize this information. So it'll be very much like we saw up here. This time, I actually put some actual numbers and real situations in this. Let's draw a larger box and make sure we have room for everything. Okay. Let's draw a couple of big circles. Okay. And so here, let's imagine the same size, that one's slightly larger. Let's say this is the number that like dogs, and the ones that like cats. And here, when I say like dogs, I mean everyone in this circle, including the spot in between, the same thing for the cats, like cats. Okay, now let's fill in some numbers. 23 people only like dogs. So within this part of the circle right here, but not including this overlap, there are 23 people in this space. Now, 15 only like cats. So in the same way, there are 15 here in this space, not including the overlap. And 7 like both cats and dogs. So we have 7 in the overlap. Okay, so both circles share these 7 people like both cats and dogs. Now, if you add those up, 23 plus 7 is 30, plus 15 is 45. We know that's not everyone. This is a survey of 50 people. That means we have 5 people out here and who like neither cats or dogs. Don't like either one. Now, let's use that then to find the following probabilities. So here's our situation. We have this information. Now, imagine taking all those names of these people and put them like in a hat or a big bowl or something, and we'll draw each one out randomly. So the question is, what's the probability that a randomly selected person from this survey, one of these 50, likes only dogs? Once again, remember that the probability in general is the number of outcomes you're looking for divided by the total number of outcomes. Okay, let's think about that. So we know in terms of people, there are 50 total people in the survey. Now, the ones we're looking for are the ones who like only dogs. How many of those are there? We know there are 23 of them. So our probability then is 23 out of 50. Okay. And once again, you can also divide that. And that's 0.46, which is equal to 46%. So 46% of the people in the survey like only dogs. Now, next, think about our next example. This time we'll say we like cats and dogs. So we'll find the probability the randomly selected person likes cats and dogs. Okay, let's think about that. So once again, we know our total number of people is going to be 50, a total number of people we could choose from. So how many of those people of those 50 like both cats and dogs? We know from our diagram and also from information, 7 of those 50 like both cats and dogs. So the outcomes we want are 7 out of the 50. And if we divide this, that's going to be 0.14, which is going to be about 14%. Okay. Actually, I need a little more space between the next couple of examples. Now, this one is where we're going to have to use our rule, our new rule. And we'll have to think about that. Let's think about this next one. It says like cats or dogs. First off, we understand that's obviously different from likes cats and dogs. So here, likes cats and dogs has to be someone who likes both at the same time. Likes cats or dogs, that can include these people like both, but also include people like either cats or dogs. So the probability of someone who likes cats or dogs and we'll probably actually show how we do this in a couple ways, because you can with a Venn diagram like this, also the information we're given, we can approach it 2 different ways. We'll show both. Okay, so from our rule over here, this is going to be the probability of people like cats plus the probability that someone likes dogs then minus the probability that someone likes dogs and cats. Okay, now let's add up those, and also we'll show why, if you just add up the number like cats and dogs, why that wouldn't be correct. Now, so actually I have to do a little bit of thinking here. So the number who like cats, we said 15 like only cats. There's another 7 like cats and dogs. So the number of people like cats altogether is 7 plus 15, which is 23. 22, rather. Sorry, 22. So 22 out of 50 like cats. Look at the ones who like dogs. We have 23 who like only dogs, but 7 who like both dogs and cats. So the ones who like dogs are the 23 here, plus the 7 here. That makes 30. So 30 out of the 50 like dogs. Now, here's the problem. Well, if we stop there, what would be the problem? Well, if you notice, we counted the ones who like both cats and dogs twice. I counted the ones who, that 7 and the 22 like cats. Also counted that 7 and the 30 who like dogs. So if I left it as it is, I'm overcounting those 7 people twice. So then I subtract off the number like both cats and dogs, which is what we found in the last example. And that was 7 out of 50. That way we don't count those same group twice. Then we put all this together then. In fact, we have a common denominator, so we actually put them all over a common denominator. So 50. So 22 plus 30 minus 7. And that then would be, let's see, that's going to be 52 minus 7. That's going to be 45. So 45 out of 50. Which is 0.9, which is going to be 0.90, which is 90%. Okay. Now, another way we can think about that, I'll say, or we can do the probability that someone likes cats and dogs. Or, sorry, cats or dogs, is if I can just simply add up. Now that I have the Venn diagram, I can simply add up all these. So combined within these circles here are the ones who like both cats or dogs, like either one. That includes the one that like both. If I ask you, if you like cats or dogs, if you're in this either circle or in the overlap, you can say yes. It's mathematically, or means either one. So what I can do then is I can just add up. So the ones who will fit my description out of the total 50, the ones who have the outcomes I like are the 23 who like only dogs, plus the 7 who like both, plus the, I believe it's 15 who like just cats. And if you put all that together, you get exactly the same 45 over 50. You can also, with the Venn diagram, you can also think of it that way. In this case, it's probably a bit easier to do it that way in the sense because that's the information, how the information was given to us. Now, last question. In fact, let's move this to the next page. How many people, or what's the probability of picking someone at random who likes neither? Okay, this is the probability of neither. Okay, so we said in our diagram up here, in our Venn diagram, we said that after we counted for all the people in these two circles, ones like either cats or dogs, that there were 5 left over out of the 50. So that 5 are the ones that don't fit into either one of these circles, so they're the ones who don't like dogs or cats, like neither cats nor dogs. And so that 5 then are the neither. Okay, 5 out of 50, which of course is 0.10, which is 10%. Now, another way, I'll just say, or another way we can find that same value is the idea of complements. So the probability of neither is the complement of the probability of cats or dogs. Okay, because if you don't like either cats or dogs, that means you don't like either one. And so, from our rules of complements, the probability of neither is 1 minus the probability of cats or dogs. Okay, and so that's going to be 1 minus 45 over 50, which is 5 over 50. So we can see we get the same thing either way. In this case, we also use the idea of a complement. Okay, so that's the idea of or. Now, let's look at another example with information stated in a different way, but the same kind of thing. So this says we have a survey of 95 men. Let me just draw a line here to separate these. We have a survey of 95 men and 104 women asked the following question. Do you like to watch football on TV? The results are given in this table below. Okay, so what this is once again, we said we also, keep in mind, we said we had 95 men. So make sure that adds up. 71 plus 24 is 95. 104 women, if you checked, 46 plus 58 is 104. Now, out of those total, this tells you how many of each, men or women, either like to watch football on TV or don't. So we're going to use this information, this table form, instead of a chart form, to answer these questions. So once again, the idea, if we select one of these people at random, what's the probability the person is male? Okay, well, let's take a look. So we know out of, once again, the probability is the number of outcomes we're looking for out of the total number of outcomes, or out of the total sample space. So we see the number of men, there are 95 men. Now, it doesn't say explicitly how many people there are, but we can add that up. That's going to be 95 plus 104, and that's going to be 199. So 199 total. And if you divide that, I'll put the squiggly lines. This probably will not come out exactly. So 95 divided by 199, that's about approximately 0.48. Once again, that's approximately about 48%. Okay. So once again, the number of outcomes we're looking for, the number of men out of the total number, 199. It's adding both number of men and the number of women. Now, if a person is selected at random, what's probably the person likes to watch football on TV? Let's think about this. And also, this last example, number 1, could have gotten that data also from the men. That's this row right here, the top row. 71 plus 24 is 95. So if you use the table here, I'll just put this as just likes to watch football on TV. I'll just say likes football for short. Okay. Once again, let's use our table to help us. So we know we have a total number of 199 people. So the question is, how many of them like to watch football? And the answer to that question was yes. So look at the yes column. We total up the ones who yes, both men. We don't care if it's a man or a woman. We just want total number of people who like to watch football. 71 plus 46 is, I believe, 117. Let's check that. 71 plus 46. Right, 117. So the yes column, add both these numbers up. That's going to be 71 plus 46 is 117 over 199. And once again, if I divide that, that's approximately 0.59, about 59%. Now, let's see what's next. This says if a person is selected at random, what's the probability the person is a man who likes to watch football on TV? Okay. So this time, this is the probability of being male and likes football. So this is a compound event. The other two are more or less simple events. This is a compound event. It's being someone who is both a male and likes to watch football on TV. So this is basically kind of like an and question. So this is where they intersect. Okay, so of the ones who like to watch, who are men, this row right here, the ones who like to watch football on TV are this column here. The intersection here, 71 out of the total. So we're saying, once again, make sure you read the question carefully. The person selected at random, what's the probability the person is a man who likes to watch football on TV? That's 71 out of the total. There's 71 who are both men and like to watch football on TV. 71 out of 199, and if we divide that, about 0.72. Oops, sorry, that's not right. 71 doesn't make sense, which you shouldn't. I put 99, so 0.99 is about 0.36. There we go. Approximately 0.36, or about 36%. Now, take a look at this next one. If a person is selected at random, what's the probability the person is a woman or does not like to watch football on TV? Okay, they ask, are these disjoint events? So this time the probability is the person is a woman or female, either way. Or, well, I'd write an O better, or doesn't like to watch football, I suppose doesn't like football for short. Okay, now let's take a look. This is an or question. So when we say, we'll make sure we don't count doubling. Also, let's ask, are these disjoint events? Let's find out. So we're saying that person is a woman. So women, we include both those who do and don't like to watch football. And then the no column is the ones who don't like to watch football on TV. So that would be basically for or, you're either in this column or that column. But if we add it up, so if we add up all the no's, that would be this number here added together. Add up all the women, that'd be these two numbers together. And that's the number of women is 104. Number who don't like football would then be 82. But if we do it that way, we'd actually end up counting these twice. We don't want to do that. So in table form, the best thing to do is simply to add this entry, this entry, and this entry. That will only count them once. So that way we're counting up. So basically it's made up, people don't like to watch football. We said or, a woman or don't like to watch football. Are the men who don't like to watch football. That would fit. Or the women who don't like to watch football, or the women who do like to watch football. All those would be valid. And so if we do that, then once again, out of the total number of 199, so we have those three entries. So 24, 58, and 46. So make sure I got those numbers right. 24, I'm sorry, 58, not 48, 58. 24, 58, and 46. Okay, and if we add all those up, that is 128 out of 199. And if we divide that, that's going to be approximately, round to two decimal places, about 0.64, about 64%. Okay. So often depending on how it's stated, it's kind of gives you an idea of which way is easier. Just remember to make sure you don't count twice. So since it's in a table form, it's easier just to count out the entries. But if we're given us the total number, instead of given us like in a sentence, the total number of people who didn't like football, and then the total number of women, then we have to make sure we counted the overlap so that we didn't count the ones who at the same time didn't like football and didn't like were men. Okay, all right. So that's the idea of kind of using or. All right, compound event. We'll take a look at the second one, the second event, which is the and compound event. Let's also mention a couple of notation, which you could have mentioned before. So I think we already said this. The probability of A and B means the probability of event A occurs in the first trial, event B occurs in a second trial. Okay. Now this other notation, probability of B slash A, you kind of read that as probably B given A. This represents the probability of event B occurring after it's assumed that event A has already occurred. And we'll see that example here in a moment. Because basically we're saying that what's the probability of event B given that A has already happened? And this is important if the probability of A happening affects the probability of B happening. In many cases, it will. We'll talk about that. So here's our multiplication rule. The probability of A and B is basically the probability of A. We assume A happens first, the probability of A happening, times the probability of B given that A has happened. And once again, now if there's no overlap between B and A, or they're independent of each other, then there's just a probability of A times the probability of B. But if A can affect what happens with B, then that's important. And we'll see examples of both cases. So once again, the intuitive way to understand this, it says to find the probability that A occurs in one trial and event B occurs in another trial, multiply the probability of event A by the probability of event B, but be sure that the probability of event B takes into account the previous occurrence of event A. Now it says two events A and B are what are called independent if the occurrence of one does not affect the probability or the occurrence of the other. And if A and B are not independent, they're considered to be dependent. Also, a few more notes here. It says when calculation, this is something for simplicity, it's kind of a general rule of thumb, not a strict rule. When calculations with sampling are very cumbersome and the sample size is no more than 5% of the total sample of the population, treat the selections as being independent, even they're actually dependent. In future videos, you may learn more about and talk more about statistical methods, statistical sampling, and we'll see that basically think about sampling, different groups from a large population. Technically, you're probably not going to sample the same group, same people twice, or most likely members of the first sample are not going to be in the second sample. That would technically, in a sense, make them dependent, but really large populations, and we have a small sample size out of the population, we can usually neglect that for simplicity, because the difference is negligible. Okay, now one more thing, we'll mention this next example. What's called sampling with replacement, selections are independent, and sampling without replacement, selections are dependent. Okay, it's a lot of words. Let's explain what that means with a couple examples. It's something you're probably familiar with cards, drawing cards. Help us understand this idea of and in this case, and also this idea of independent and dependent events. So let's take a look at this very first one. What's the probability of drawing two kings in a row from a standard deck with replacement? Okay, and what does with replacement mean? With replacement means I, of course, shuffle the cards, draw a king out, let's say. Okay, then I put that card back in the deck and reshuffle them as if I never drew a first card in the first place. That's what with replacement means. So in other words, these are independent events because the first draw is not affecting the second draw. So these are independent. Okay, and first draw doesn't affect the second. Because once again, it's called with replacement. So I'm putting the card back in, reshuffling the deck as if the first draw never happened. Let's think about that. So this then, so the probability of I'll just put as K, king and another king is going to be just the probability of a king in the first draw times the probability of a king in the second draw. Okay, and this is my first draw, and this is my second. Once again, that's a K there. Let's calculate those. And here, my this is still, you think of this as probability of drawing a king on the second draw, given drew a king in the first case, but since with replacement, it has no effect. The first draw has no effect on the second. So what is this? Well, think about a standard deck has 52 cards. Then how many kings are in the deck? Well, there are 4 kings, so 4 out of 52. Now, that's the first draw. Now, the second draw, saying I draw a king on the first draw and a king on the second draw, what's the probability of that? Well, since these are independent, and as if the first draw never happened, and the second draw is like just like the first draw, there's still 52 cards in the deck, and out of those 52, 4 are still kings. So what I have here then is going to be 4 times 4, multiply across fractions, 4 times 4 is 16, times 52 times 52, which is 2,704. And then if we approximate that, it's going to be a fairly small number. Yeah, so this, in fact, is approximately, I'll go to 3 decimal places this time, 0.006, okay? Or about 0.6%. Not 6%, but 0.6%. Because remember, to change from decimal to percent, move your decimal places 2 places to the right. So less than 1% chance of that happening. Now, let's see how it's different when we do what's called without replacement. So without replacement, as you could probably guess now, means that I take the card out. First draw, I say I'll draw, assume I draw a king in the first draw, but I leave that card out of the deck. Okay, so now, as you can imagine, there is 1 fewer total cards in the deck, only 51 cards in the deck now, and there's also 1 fewer king left, only 3 kings left. So this makes it, this is a dependent event. Because the first draw does affect the second draw. So it does affect the second draw. And we'll see how. Okay, so this time the probability of a king and a king. So if we write it kind of the way it's shown here, this is going to be the probability of a king times the probability of drawing a king on the second draw, given that I drew a king on the first draw. Okay, now in the previous one, we just wrote it as the same thing because, once again, since with replacement, it's as if nothing changed. So it's the same probability as drawing a king the first time out of a regular deck with no draws before in each case. In this case, it's different. Okay, and so once again, this is, of course, is my first draw and my second draw. Now let's see what happens. Let's see how that's affected. So once again, the first draw is the same in both cases. There are 52 total cards and 4 kings. That's probably drawing a king in the first draw. But now, as we said, what happens? Without replacement, it means I leave the card out of the deck. Even reshuffle the deck. So now what happens is there's 1 less card, 1 fewer card, only 51 cards total in the deck now, leaving that one out. And now, assuming I drew a king the first time, there are only 3 kings left instead of 4. So you can see this has an effect. So if I multiply that, 4 times 3 is 12, and then 52 times 51 is equal to 2652. So 2,652, and if I approximate that, we'll see how it compares. And this is also, I'll go to 3 decimal places as well. So 0.00, about 0.005, which is about, once again, 0.5, approximately 0.5%. So actually, your chances of drawing a 2 kings in a row with replacement are actually larger, slightly larger, than drawing 2 kings in a row without replacement. That's the idea of without replacement and the idea of independent and dependent events. So if the first event, or not just the first event, but preceding events have an effect on following events, that's called dependent. And basically then we have to take into account what's happened in the first or in previous events, then determine the current event, what its probability is, because it can be affected by that. I'll write that better, it's more like a squiggly equal sign. There we go. Okay, so what we've learned today is that we have compound event is where we combine, as it sounds, combine simple events. In the case of or, if it's probability of A or B something happening, we have to, it's a probability of event A plus a probability of event B minus any overlap. If there's no overlap, then they're called disjoint or mutually exclusive. And sometimes depending on a table or a Venn diagram, sometimes it may be easier just to add up the individual parts to make sure there's no overlap. And then if we have a compound event where it's a sequential, where one event happens after the other, like drawing cards from a deck, then first event is the probability of A. If event A happens first, it's first the probability of A, then times the probability of B, given the day has happened. If A doesn't affect B, then they're independent events. And but if A affects B, they're called dependent, and then we have to take into account to understand how A happening can affect B happening. So that's the idea of the probability of compound events. Thank you. Have a good day.